Welcome. Today's notes worksheet is entitled Complex Zeros of Polynomial Functions. This lesson offers us an opportunity to solidify some of the ideas and skills that we've been developing over the last few notes worksheets. So we'll go ahead and start the process with a little review at the top and see where it develops from there. Obviously, you've seen over the last few lessons that what we need to be able to do is solve a quadratic equation without too much difficulty. So the idea is to break down these polynomials until we get to the quadratic stage and then pretty much solve through more of our traditional means, either factoring or undoing the square or completing the square, something along those lines. So let's start at the top and do the review. 3 quadratics. And so I've got x squared plus 3 equals 0 to start it out here. And this one's really not too bad in that it is a candidate, certainly for just undoing the square. So I think what we'll go ahead and do is just subtract 3 from both sides, bring that on over, and we get x squared equals -3. Really not too bad right there. And then undoing the square in order to get the variable by itself. So let's go ahead and do that piece right there. And of course, square and square root cancel, which is exactly what I wanted. And I definitely get my x equals. What I would love for you to do is to write what you think the solution set is just on the other side here. And then I'll just wait a second and go ahead and do that as well. So remember, taking the square root of a negative, of course, does mean that we want to factor out that I. And undoing the square as well means we do want a plus or minus. So let me get that out in front. And I hope everybody pretty much did an I root 3 there. So positive I root 3 and negative I root 3 would be your 2 values that make this equation true. There we go. Not too bad to start it out. So obviously what we have here is a couple pure imaginary numbers. Let's go ahead and do part B, a little more difficult in nature. I can't undo the square, of course, because of this 4x right here. I would tell you up front that this does not factor. And so I think we're left to completing the square in order to get the exact values here. So let's go ahead and do that. I have x squared plus 4x. Always complete the square from the first 2 terms. And we don't have a value in front of the x squared, so that's kind of nice. And then I'm going to bring that 10 on over. And I'm going to put my blank on the other side as well there. All right, looking pretty good. At this stage, we should be able to complete the square, pretty regularly. In this case, I would go ahead and take the 4 and divide by 2, which gives us 2. And 2 squared, of course, is then 4. Whatever I do to one side, absolutely must do to the other. Make sure you do balance that out nicely there. And the whole reason for completing the square is to create what is called a perfect square trinomial. And this factors in a very particular way. It factors into the square of a binomial, so a binomial times itself. And if I did ask you to factor this, I think everybody would probably agree it would be x plus 2 times x plus 2, better expressed here as x plus 2 squared. Sounds great. Let's clean up this other side. Again, not too bad there. Just gives us a -6. All right, now it's in a good form. Let's go ahead and square root both sides to get rid of that square first. So I undo the square, and when I do it on the left, I get my x plus 2. When I do it on the right, as we saw in the last example, don't forget the plus or minus. Pull out the factor of I, please, and we get I root 6. Looks good. Only one additional step at this stage. Everyone take that 2. Let's bring it on over to the other side. When it does cross the equals, it becomes negative. So something along these lines would be a good expression of the solution set right there. -2 plus I root 6 would balance that equation. And -2 minus I root 6, if we put it in, would balance that equation. All right, very nice. 2 review problems down. What do we say we try that third one right up here, a little harder? If it helps you with this one, go ahead and throw a little 1 right in there. It's not mandatory by any means. And let's go ahead and complete the square. Again, doesn't factor. So in this case, I kind of have a 1x. Sometimes without that 1 there, I see students get a little confused on how to complete the square. So I'll put it in just for visual assistance. Bring that 1 on over to the other side, and it becomes -1. And don't forget, of course, we need to balance. So the question, of course, for this one is, what are we going to use to complete the square right here? And let's take that 1. So that b value is 1. Divide it by 2. 1 divided by 2 is 1/2. Square 1/2, everybody, if you would. And I hope everybody is comfortable at this stage with me throwing in a 1/4 right there, which means, of course, Let's throw the 1/4 on the other side. Excellent. Now we do want to factor this. Again, it is a perfect square trinomial, so it is something times itself, so a binomial squared essentially. X times x would give us this x squared right here. You're asking yourself, what times itself would give us 1/4? Hopefully 1/2 sounds good to you. 1/2 times 1/2 would give us the 1/4. And it had to add to 1 in the middle, so plus in the middle there would work. Okay, so x plus 1/2 times x plus 1/2. Now the other side is -1 plus 1/4. Fractions here, of course, everybody. -1 would be -4/4. So if it helps you, kind of write that in there. -4/4 plus 1/4. And again, not too bad, hopefully, but -3/4 would do. All right, we're in a pretty good position. Let's pull it off. So square root both sides. So undoing that square right there gives me x plus 1/2, of course. Now this one as a fraction, let's see if we can take it piecemeal here. I do the plus or minus, of course, out in front, just automatically. And then I think of it as sort of pulling out a factor of I. That'll sort of go on top, for lack of a better spot for it. But you could throw it out in front. And then root 3 really can't be touched. But square root of 4 is definitely just 2. So I'm seeing this simplified pretty nicely into an I root 3 over 2. Really nice. And then as a result, you can kind of see a common denominator here with these two, as that 1/2 does move over to the other side. And when it does, of course, well, we're basically subtracting it, so it becomes negative. And I'm going to write it like this. If it throws you off, please put a little asterisk by it and ask. But essentially, that would be a good solution set right there. All right, so all types of solution sets for these quadratics. And we're going to definitely see that along the way as we build up to the cubics and quartics and quintics and so forth. All right, good little review. Let's go ahead and get started on the next piece. And as you can see, just sort of 3 theorems here to just take a look at. The nice thing about these notes worksheets is it's all right there. We just kind of have to go through it and read through and just make sure we understand this piece. Obviously, the big one here is what's called the fundamental theorem of algebra. And I think we kind of knew this intuitively, and we've been developing this over the last few lessons. And so let me go ahead and read what I have and see the little mathematical example here. So first and foremost, a polynomial function. So a polynomial function of degree n has exactly n zeros. Okay, so again, I think we kind of knew that to be the case. So a quartic polynomial function has exactly 4 zeros. A degree 7 polynomial function has exactly 7 zeros. Okay, functions have zeros. And again, by the same token, just a different way to phrase really, an equation in a single variable has exactly n roots or solutions. Again, we've talked about the phrasing before. Zeros of functions, roots of equations. And again, this includes, we have to be careful here, complex and repeated solutions. So like, for example, we all know every quadratic equation, and that's what this is right here, a quadratic equation has 2 solutions to it. And that includes the idea of repeated solutions. So this obviously is 1. I know it's the same number, but it occurs from 2 factors of x minus 1. So we would call this a double. And again, we've seen that before. So every quadratic has 2 solutions. All right, perfect. Let's go on to the linear factorization theorem, which really is just sort of a corollary of this one up here. Factors and zeros go hand in hand. So a polynomial of degree n has exactly n linear factors. Exactly. And so the case right here, of course, is we have an example with a cubic. And every cubic can be written as 3 linear factors. And you see I kind of did that right here. This one happens to have a constant, a leading coefficient of 3. But the linear factors, boom, boom, and boom. Those 3 multiplied together would give me this in standard form. And again, I think we just knew that intuitively. Last one on the sheet here is what's called the conjugate pairs theorem. And it says if a polynomial has all real number coefficients, and really for our purposes, those are the ones we're focused on, then complex zeros appear as conjugates. Absolutely. And we saw that with, as a matter of fact, the 3 review examples that I gave you at the top of the page. So something simple like this. if we're going to get complex answers to an equation like this, they're going to appear as conjugates, positive I and negative I. And I'll be very fast, and then we'll move on from here. Take a look at the 3 right here. All of these were in the complex number system, and as you can see, conjugates of one another. Perfect. Okay. Well, let's use those ideas over the course of these next examples and see if we can just feel pretty good about it. Just reinforce many of the ideas that we've been developing. All right, let's start it out. Example 1. Given that 3i is a root of the polynomial equation, so here, guys, I've got a quartic equation, and 3i is one of the solutions to it. Find the other ones. All right, very nice. So I haven't given you one of the answers in a while. We've been just kind of developing them ourselves. So in this case, I'm going to start it out with understanding that 3i is one of the answers. And so in order to find the other ones, we're going to use our little synthetic division ploy to break this polynomial on down. And this is an interesting one because we haven't really used synthetic division with an imaginary value right here, but certainly feasible. So let's go ahead and make it happen. So I've got the 3, 5, 25, 45, and negative 18. Let's run those across, everybody. And let's see what we can do with this. So interesting. Bring down the 3. And remember, we multiply diagonally and add vertically. So 3i times 3 is 9i. And then this is going to be intriguing. We're going to add vertically, and 5 plus 9i is exactly that. 5 plus 9i. All right, and now it gets a little hairy, huh? Actually, we're fairly fortunate. I mean, this is not the best value by any means, but it would be even worse if it wasn't a pure imaginary and it was just a full imaginary number like 1 plus 3i or something like that. That would be even worse. But in this case, let's see what we can do with it. So I hope you would agree that we're going to multiply this into this right here, and it's going to produce an imaginary part, 3i times 5, and it's also going to produce a real number part, 3i times 9i. So let's do that one first if it's okay with you. So 3i times 9i, 3 times 9 is 27. I times I is I squared, so we get 27i squared. And everybody, what is 27i squared? Hopefully you remember that. I squared is negative 1, so 27i squared is negative 27. And then 3i times 5 is 15i. Again, ideal? No. But can we do it? Yeah, sure. All right, let's add. So 25 plus negative 27 should give us negative 2, and then add the 15i. That's looking pretty good. Time to repeat, everybody. So imaginary part will come from multiplying these. Real part will actually come from multiplying those. So 3 times 15 is 45. I times I is I squared. So 45i squared is negative 45. And that's interesting that it played out that way. And then let's see, 3i times negative 2 is negative 6i. Add going down, everybody. Those obviously kind of cancel out, and I just get a pure imaginary at negative 6i. Beautiful. And you probably knew this was coming because when I multiply these two together, I get negative 18i squared, which of course is 18. And that needed to happen because I gave you 3i as a root, and so we did expect, obviously, the 0 as the remainder. Super. All right, now, no graphing calculator here. But where do we go? So what I need you to do is think about the next step. We went from quartic to cubic. And look at our coefficients. My goodness. That looks scary. So how can we fix this? What's the remedy to this situation here? Well, if you look above, it's not like I gave you one root to the equation. I actually gave you 2. So think about what that second root must be based on what you see above on your paper there. And if you think about it, if 3i is a root, then negative 3i is also a root. Because, here, let's go back to it really fast. Conjugate pairs theorem right here, everybody. If a polynomial has all real number coefficients, which ours did, complex zeros, which we have, always appear as conjugates. And so if 3i was a root, then negative 3i, its conjugate, has to be a root as well. And so now we're ready to roll. Let's go ahead and pull this off. Everybody bring down that 3 and watch how nice this is going to work. The scary part's over because when I multiply here, I just get negative 9i, and I add going on down, and as you can see, these are going to cancel, and I just get 5. Even when I multiply here, guys, I get negative 15i, add it on down, and I get negative 2. Should not be a great surprise here, but when I multiply those two together, I get 6i, and then there's my remainder is 0. And as you can see, quartic, cubic, quadratic, looks great. This is our goal, to get to this stage, because now we can solve through more traditional means, and that one right there. So we would run through our options, of course, factoring, undoing the square, completing the square, etc., maybe even a little quadratic formula if necessary. In this case, I will tell you it factors. So take a moment, if you would, and factor that equation, and let's get all the roots to this equation at the top. Okay, so here's what I have when I factored it. Took those, I broke it down. Looks like 3x and x would do the trick. Obviously 2 and 1 here, and looks like that's going to be our way to do it. And how does a +2 and a -1 sound to you? Check that out. Just make sure you agree with that factoring right there, because then when I take those factors and set them to 0, as we've been doing for a while now, not too bad, I get x equals 1/3 on this end, and x equals -2 on that end. So when I go ahead and write all my roots, it looks like the plus or minus 3i appearing as conjugates as we expected. And how about the 1/3 and the -2? All right. Good. So nice one there. A little synthetic division with imaginaries. Kind of cool. All right. So I think we should use the graphing calculator in this next piece to kind of get us started here. But essentially what we now know, for example 2 in particular, is this quartic has 4 zeros to it. So we're going to find the 4 zeros. And again, we're going to bring up our calculator to go ahead and get us started here. So if you can grab yours. And the idea is, rather than just kind of doing synthetic division blindly and hoping for the best, I don't want to spend our time really doing that. I want to spend our time with the skills that are required here. So let's type this in. And if you could do it as well, that would be great. Just want to make sure I get it correct for you. And plus x. And how about the -2? Looks good. Zoom standard. So we could develop our P over Q list, and that would look great, and it'd be a lot of fun. And we would test blindly and try and hope and all that. But I think we want to expedite the process a little bit. So I graph it on the calculator, and I look for those rational zeros, those P over Q values that do work. And it looks like -2 happens to be one of those. And it looks like +1 also happens to be one of those. So we can get a couple of these quickly from the calculator. Saves us the time of energy of just trying them out and hoping for the best. So I saw +1 as one of the rational values, one of the zeros of this function. And obviously we know that would be a P over Q value here. And let's go ahead and use that to break this on down. So again, really should be able to pull this off using the technology, using the technology and integrating that into the problem solving here. All right, guys, let's be quick with the synthetic division. Bring that on down. I get this. Again, nice and fast on that end. Sounds good. Quartic to cubic. And, sometimes, every once in a while, you can get a cubic that can be broken down through more traditional means. I see this. We actually can solve straight up. But I'm going to go ahead and take the approach that we've been looking at here with the synthetic division. So I did see -2 was also a zero of the function. Saw that from the graphing calculator. So as a result, I'm going to go ahead and use that. Took the time to graph it, so I might as well use what I found on the graph. Bring down that 1, and let's go for it again. Okay, and not too bad because I get this piece right here, exactly what we expected. And as you can see, quartic, cubic, quadratic. And so we're left with x squared plus 1 equals 0 to get the remaining 2. So 1 was a 0, negative 2 was a 0. I didn't see any others show up on the coordinate plane, so the other 2 have to be pure imaginary, and obviously that's what we're going to get right here. So square root both sides, and I hope you'd all think of that as plus or minus I. So square root of negative 1 is I. Don't forget to take both roots though. And so as a result, zeros of this function look to be 1, negative 2, and there are our imaginaries showing up as conjugates of one another. Okay, nice. Let's do another. We got quartic taken care of there. What do you say we try a quintic? So find all of the zeros. So I'd ask the question, of course, right off the bat for example 3. How many zeros are we going to find for this quintic? 5 of them, 5. Let's see if we can get a couple at least from the graphing calculator, and again, just see where it leads. So I'm going to clear this out. Everybody type in with me if you would, please. I've got my 3x to the 5th, etc. right down the line there. Again, you're probably quite a bit faster at typing in than I am, so bear with me if you would. Okay, getting closer. And there we go. All right. So you hit graph, and it looks like I've got a couple to work with here. I see this, and just looking at the P over Q's, it looks like negative 2. I'm pretty confident that that's a negative 2 right there. That's definitely a P over Q value. Just coincidence, but I see the 1 popping up again, along with that negative 2. And then I see another one right in here. We're going to have to kind of deal with that one. I'm going to start out, if it's okay with you guys, with the negative 2 and the 1, and then we'll find out what the deal is with that one right there in just a couple minutes. So let's start out with the 1. So let's go ahead and do our synthetic on this. Remember, guys, quick but perfect. Okay, so run those numbers across. Let's bring it on down. Here we go. The 3 comes down. Got that. Looking good. All right, super. 1 down, obviously the 1 is a 0, and I've broken it down a level, quintic to quartic. I believe I found negative 2 to be another one there. So let's use negative 2. Same deal, everybody. Let's go ahead and take care of that piece. The 3 comes down, and let's do a little more synthetic on this. Again, nice and quick with this, everybody. Feel good about that algorithm? Perfect. All right, so now I'm down to cubic. Again, if anything piques your interest on that cubic, you can certainly explore it, set it to 0, and see if you can solve. But I'm going to go back to that graphing calculator, and there was that third one, which was right in here. And so I'm not sure because it's in between 0 and 1. It's a little tough to tell. Is it rational or irrational? So I'm going to go ahead and find out what it is. So I go second trace, of course, and do my 0. And let's see, it looks like I am to the left of it. There I am. So it popped up to the left. And, you know, wherever you are on your graphing calculator, make sure you do just set up a left bound and a right bound, hit enter on it, and lo and behold, it looks like it's 1/3. That's great. And as you can see, 1/3, just from the original function there, 1/3 is definitely a P over Q value. So that's it. I like it. So if you're not sure, of course, with 1, check it out. See if it's rational or irrational. If it's rational, go for it. If it's irrational, there's not much we can do except maybe explore an alternative. Okay, well, let's see what we've got. Bring down the 3. Got that. Looking good. And there it is. Perfect. So quintic, quartic, cubic, down to quadratic. Now we take the quadratic and solve. Let's go ahead and do that together. Bring the 27 on over. Divide by the 3. Undo the square. I'm going to just have to come up here. And it does look like we end up getting plus or minus on the root negative 9, which would be 3i. So 5 zeros, 3 of those nicely from the calculator there, and then those 2. In this case, just again coincidence, especially relating it to the last one, that they're pure imaginary. But any type of quadratic you should be able to solve and get them if they're complex. All right, so example 3, very nice. Let's see if we can develop a couple other ideas here about zeros, just in very general terms with example 4. So it says, determine the possible number of real zeros and the possible number of imaginary zeros for each function. And notice what it says here, everybody. Let's just be clear about this piece. This is not Descartes' rule of signs. So Descartes' rule of signs just really specifically talks about real numbers, and it talks about possible positive and negative. Now this certainly is connected to that, but it is not Descartes' rule of signs. It's just really talking in very general terms about real zeros versus imaginary zeros for any polynomial function of n degree. So here's what I'll have you do. Let's just do real and imaginary. And let's just start talking about possibilities. Now we have enough to just at least have a discussion about this, especially starting out with this cubic. And I started out nice and easy here. A cubic, as we all know, has 3 zeros, right? So the question is, what is the composition of those 3 zeros? What are the possible combinations? Well, I hope everyone would be in agreement with me that theoretically all of them could be real. So out of the 3 right here, we could have a situation where there are no imaginaries and just all 3 are real, right? That would be one possible combination to get those 3 zeros. And that one I'm hoping is fairly straightforward. It is possible that all 3 are real and we wouldn't have any imaginaries. Okay. Put a little or behind it if you would, because that's not the only possible combination. Now here's what I would ask you. Is it possible to have 1 imaginary and 2 reals? Think about that for a sec before writing that in. Is it possible out of those 3 zeros that there's only 1 that's imaginary and 2 real? And the answer, of course, is, as I get my eraser here, no. That is not a possible combination. And the reason, of course, is I can't have 1 imaginary number because of, sorry to go back a couple screens, this right here, everybody. Remember the conjugate pairs theorem? They have to appear in pairs. So those imaginaries have to appear as conjugates. And so as a result, you can't just have 1, but you can have 2. You can have a pair of imaginaries, which would mean, of course, then the other one is real. So it's either going to be 3 real and 0 imaginary, or 1 real and 2 imaginary. That's it. Those are the only possibilities. You cannot have 3 imaginary zeros because the imaginaries show up as conjugate pairs. All right, good. Let's go ahead and try B. Obviously, now I upped the ante quite a bit here. Degree 8. Let's think about all the possible combinations and go from there. Okay. So first and foremost, I hope you would all agree that theoretically all of them could be real, and you could have a degree 8 polynomial with no imaginaries. Absolutely. That is one possible combination. Well, the other situations that emerge obviously would be, based on the conjugate pairs theorem, that the imaginaries have to show up in pairs. So theoretically, I can't have 1 imaginary number, but I can have 2. And if there are 2 imaginaries, how many reals would that be for this particular function? Well, remember, there have to be 8 total. So this is a possible combination right there. A pair of imaginaries and the other 6 real. I can't have 3 imaginaries, but I can have 4. I can have 2 pairs of imaginaries, which would mean if I do have the 2 pairs of imaginaries, then the other 4 would be real. And you could start to see what goes down. These go down by 2s. These go up by 2s. I could have 3 pairs of imaginaries. Or I could have 4 pairs. I could have all imaginaries here because it's an even degree and no reals. That is possible in this case. So hopefully that development works for you as we go ahead and make some type of conclusion out of it. But in essence, you start to see that for real numbers, basically I can have n real zeros, right? I can theoretically have all real zeros. So I can have n, but then they start going down by 2's. Where the imaginaries, I can only have either 0 of them, or 1 pair, or 2 pair, etc., etc., etc. So just kind of keep that in the back of your mind, how those work in conjunction with one another, real zeros and imaginary zeros, based on the fact that there are n zeros for every function. Okay, very cool. Let's go do a little graphing calculator work on the next one, and then start to bring this to a conclusion. Example 5. It says graph each function on the calculator. Based on the graph, determine the types and number of zeros for the function. Okay, good. So what I'm looking for here is just based on what we see, are we getting rational zeros, irrational zeros, imaginary zeros? And just if you would, somewhere right around here, if you can, let's just go ahead and write real with these two. So remember, real zeros are made up of rational numbers and irrational numbers, and then obviously the imaginaries being separate. Well, let's see what we can develop here. So just graphing calculator only. No other math required for this. So let's type it in. I'll look at the graph and talk to me about zeros. That's what I'm after here. Okay. So what do you think in this case? It's cubic, so we know there are 3 zeros. And notice what showed up here on the graph, 1, 2, 3 x-intercepts, so 3 real zeros. So right away, I know that for this particular function, there are no imaginaries. And so in this case, I guess we can just figure out, are they rational or irrational? And as it turns out, as a matter of fact, each of these values, as you can see, would be on the P over Q list. This looks to be -4. That's -1. This looks to be 4. All values on a P over Q list for this function. And so as a result, it looks like all 3 happen to be rational. And again, we could check it further if we really needed to. So 3 rational, 0 irrational. And of course, we already made the conclusion 0 imaginary. That would be the composition of the zeros for that function just based on the graph. Okay, very cool. Let's go do the next one. So I have x to the 5th minus 4x cubed and minus 5x. Hit graph. Notice right here, of course, it looks like we have 3 real zeros, and so this is a quintic. So can you probably tell me how many imaginary zeros there are to this function, just looking at the graph right there? And it looks to be 2, because there are 3 reals, and so the other 2 have to be imaginary. This one is 0 right here, which of course would be rational. Now these 2 right here, it doesn't look like it's right at 2, by the way. It looks like it's a little past 2. And the question is, if you were to make a P over Q list, and this one's interesting because 0 is a 0 of this function, which means that x can be factored out. So once you take x out, and don't do this on your paper, but then we're left with this, then start thinking of P over Q values for this one. And notice it didn't look to be exactly 2. So if you could make up a little P over Q list using that the 5 on the back, do these numbers look like they would be on a P over Q list? No. And so if they're not on the P over Q list of this, really it would only be plus or minus 1 and 5. Those other 2, without even checking on the calculator, have to be irrational. So I see 1 rational, 0 by the way, that was the rational. 2 of them, the other ones were irrational, and hence the other 2 were imaginary. Pretty cool composition right there. That looked great. Okay, let's go ahead and do letter C. And so let's go quartic on this. X to the fourth, 5x squared, and of course add the 6. And something, I suppose, somewhat parabolic in nature there. Tough to tell, but it looks like that's it right there. What would you say on this one, by the way? There are your real zeros. And by the way, this is just going to keep rising to the left and rising to the right. Any real zeros? No. So it looks like all 4 have to be, let's do this. All 4 have to be imaginary. So none of them are real. So 0 real, and all 4 have to be imaginary. All right. Hope it's kind of clicking here. Let's go ahead and maybe do one more. Got that 4th one right there. So last one looks to be cubic. So 3 zeros. And let's go x to the 3rd on that. 8x squared plus 20x and minus 16. Keep your eye on what would be a P over Q if you can. And this one's kind of interesting, and I'll just tell you to expedite this along. This is a touch at the 2. So think of that as counting as twice. So a double on the 2, and then one at the 4. 2 and 4 definitely are on the P over Q list. So even though this is a touch, it does count twice for the 3 zeros, and the other one was a single. So it looks like a double on the 2, single on the 4, and those are all, oops, let me get that right for you. I was thinking one thing, wrote another. Rational. All right, looks great. Hey, let's just do the last piece here. Example 6. Determine the zeros of example 5C. Oh, okay. That was interesting. So that was the one that were 4 imaginaries. And we didn't get any from the graphing calculator like we did on some previous examples. So is it feasible to do synthetic division using any help from the graphing calculator? No. I don't want to do a P over Q list. We already realized that there are no real numbers that work here. So let's just see if we can solve this a little more traditionally. So this one here, again, no help with synthetic, unfortunately, because there's nothing to use. But it does kind of factor. We've seen this maybe once or twice before, where it has that quadratic feel to it. So x squared and x squared. And then let's think about this. It looks like probably a 2 and a 3 on this end. 2 numbers that multiply to 6 and add to 5. And so really I kind of broke it down myself here into 2 binomials. And then I take each one of those and set them to 0. And so you can kind of see that even though the graphing calculator wasn't any help, I'm just going to go ahead and get our 2 values right up here. It looks like I root 2, so 2 pure imaginaries right there, and 2 more pure imaginaries right here. And there are your values. So again, a little contrived in that end, but still, we weren't able to do synthetic on it, but we were able to pull it off just factoring. Okay, some good stuff here to develop. Let me know if you have any questions along the way, and certainly thank you so much for listening.